All right, hey everybody. So I am going to be teaching you the next or the second optional lesson that you don't necessarily have to know for the AP exam because it's been cut out, but something again I think is pretty helpful, and that is the comparison test and the error bounds with comparison test. So hopefully by now you know the mandatory ones, which are alternating series test and ratio test, and maybe you've already learned the integral test as well. I'm going to finish things up a little bit here with comparison test and how that one works. I like comparison test. I think it's very helpful. The way we utilize it is definitely using p-series. And this is normally the lesson where I teach p-series. So I kind of put on the screen here again for you what p-series are. We've already done these notes in our first mandatory lesson on alternating series day. We learned about p-series. But we know by looking at a series that is a p-series in the form 1 over np, we know that it's going to be convergent if p is greater than 1, and divergent if it's less than or equal to 1. So that's an easy thing to be able to tell if it converges or diverges, and we're going to use that knowledge to help us compare it to another function, use the comparison test, and identify if that function converges or diverges. Okay, so I'll let you look back over that if you need it. That's yours. So let's move on. Okay. Um, First things first, we've learned comparison tests before, but it wouldn't help to maybe, or wouldn't hurt to maybe refresh it a little bit. We learned it with like functions. We never really learned it with sequences or series yet, but we can definitely talk about that right now. It says the comparison test. Suppose that we have some series summation a sub n and another series summation b sub n, and the series with positive terms. The a sub n, that's going to be my given, okay? And the b sub n is going to be the one that I create in order to compare. All right, the one that I create in order to compare. And whenever I'm creating this, the idea is to create an easy function, all right, that I know is either always bigger or always smaller than the series that I'm given in order to figure out if the other series converges or diverges, okay? And the one we create is either going to be p-series, or actually it's going to end up also being a geometric type as well. Either one is going to be very beneficial here, okay? All right, now, like I said, you've seen this logic before, but let's refresh ourselves on what each of these cases are for the comparison test. All right, if b sub n, all right, the summation of b sub n, which is the one that I've created, all right, if it's convergent and b sub n is also greater than a sub n for all of n, then a sub n is also convergent. Let's draw that out real quick. All right, so here's b sub n, and I'm saying b sub n is convergent. And I'm also saying that b sub n is greater than a sub n for all of n. If that's the case, then a sub n must also converge. I think that's pretty straightforward. And vice versa, if we have b sub n, and I chose b sub n to be divergent, meaning it's doing this right here, okay? Well then, if a sub n is greater than b sub n for all of n, then that must force a sub n to also be divergent, okay? So again, we've seen this before, we've used this before, and you'll see that it's pretty easy to create it once we start getting the hang of it. But yeah, so right here it says the comparison test applies only to series whose terms are positive. So that's usually, it's got to be above this line right here, the x-axis. And these are just, again, putting it into two different phrases, what's being said above. Okay, so let's jump into one example. All right, it says determine whether the following series are convergent or divergent. And comparison tests can be used in a whole wide variety of different things, as well as other tests. I try to use it in a rational situation. All right, a rational situation that has maybe like some polynomial or some like square root in it or something along that form. Okay. Um, and oh wait, I think I skipped a slide actually. I did skip a slide. I apologize. I skipped this slide. Um, this slide was meant to practice all of the types of tests that we have so far. And I'm not going to go through and do all these because, again, it's just review, but I'll tell you the test that I used to help me. Here you can identify convergence based off of p-series. It's very simple and straightforward. I used integral test for this one if you want to practice that. I converted this into a geometric series to identify if that converges or not. Believe it or not, I actually used p-series here as well. Because the top is oscillating between -1 and 1, so that's like almost like that's not increasing or decreasing in any direction, so I can just compare the p-series. I converted this to a geometric series as well, and I actually decomposed this and split it up into two separate rationals. I did n times n squared plus 8. And I decompose that into a over n plus bx plus c over n squared plus 8. So if you want to try that, you can. But again, I want to jump more to comparison test problems, which is like this one, if I can get to it. There we go. All right. So it says determine whether the following series is convergent or divergent. Like I said, I like to do it whenever you have like some polynomial and a rational. I think that's pretty okay. So what's going on is this function right here, I'm going to treat this as a sub n. So I need to create a b sub n to compare it to. Okay. The thing is like whenever you create b sub n, it's all you got to create a function that you can clearly identify as always greater than a sub n or always less than a sub n. Okay. So I usually try to build it based off of like kind of my leading coefficients here. So I'm seeing that we got b sub n equals 5 over 2n squared. And I try to think about it if I can without the coefficients. Okay, so like 1 over n squared. So there we go. 1 over n squared. 1 over n squared is a p-series. So I know that this p-series, okay, which p is equal to 2, which is greater than 1, I know that this is going to actually converge. Okay. And knowing that that converges, if I know that converges and I can guarantee that b sub n, all right, is indeed greater than or equal to a sub n for all of n, then I can use the comparison test to say that a sub n converges. Okay, and we're not going to spend too much time like talking about how to identify a sub n and being greater than or less than b sub n. It's going to be more based off of logic. Like in this case, if I'm comparing this sequence to 1 over n squared. All right, well, over here, depending on what I do, like whatever I plug in for n on the denominator, that value is going to be much bigger than the denominator for n squared. So if that's the case, that if I have a bigger denominator over here on the left side, then that means that I have a smaller fraction, therefore being less than 1 over n squared. Okay. Now this correlates with the comparison test. I know that b sub n is convergent, and I also know that it's greater than a sub n, so therefore a sub n also converges. So how we like to write it. And since I classified this as a sub n and this is b sub n, I'm not going to rewrite them. I'm just going to call them a sub n and b sub n. So I'm going to say since a sub n is less than or equal to b sub n, and the summation from n equals 1 to infinity of b sub n is convergent. So remember, that's my p-series. Okay, that's the criteria I need to use the comparison test. I know that this is true and this is true. And if that's true, then by comparison test, the summation n equals 1 to infinity of a sub n is also convergent. And there you have it. Boom. Okay, that wasn't so bad. You can pause it and kind of read through that and take down the notes if you need to, but I'm going to go ahead and jump into the next example. Okay. and it's 1 over n squared plus 2n. All right, now again, I'm kind of recognizing that I got like a rational, I got a polynomial in there. I'm thinking maybe I can come up with a p-series or a geometric sequence. In this case, I would do a p-series that I can compare to it and talk about the convergence. So like if this is a sub n, I'm going to create b sub n, and I try to create b sub n based off of the leading powers. So I'm going to say, all right, how about I'll make b sub n be 1 over n squared, which again, this is a p-series. Okay, p is equal to 2, which is greater than 1, and therefore is convergent. All right, so if I can show that b sub n is greater than a sub n, then I can also guarantee that a sub n is convergent. Okay, if I can show this, like I got b sub n being convergent, if I can show a sub n is also convergent, all right, then by comparison test, or I'm sorry, if I can show that a sub n is less than b sub n, by comparison test, I know that a sub n is also convergent. Okay, and again, I'm not going to do too much logic or too much math with that. It's going to be all based off of logic. 1 over n squared is bigger than 1 over n squared plus 2n because this has the additional plus 2n piece to it. So therefore, the denominator is going to be a lot bigger, making this fraction a lot smaller, making this inequality true. Okay, so we can say the criteria again. We can say, hey, since a sub n is less than or equal to b sub n, and it can be equal to or less than. Since that's true, okay, and the summation n equals 1 to infinity of b sub n is convergent. So the one I created I knew is convergent, and this matches. Like these two things match. Okay, since that's the case, then by comparison test, all right, the summation n equals 1 to infinity. I believe that started at 1 in the problem. Yeah, it started at 1. Summation n equals 1 to infinity of a sub n is also convergent. Very nice. Very nice. Okay. So again, just like all these other tests, the more practice you do, the better you get at it. It's going to be very procedural in these steps. Let's try another one. Okay, I got one more I want to try before we move on to something else. All right, we got the summation n equals 1. N equals 1 to infinity of 1 over the square root of n minus 4. So this is still kind of in a form I like to use comparison test. And if this is a sub n, I need to create b sub n. Okay, and I need to create b sub n. And again, I'm gonna take the leading powers again. And I'm gonna use that as my created function to compare. Okay, so I'm gonna say that b sub n is 1 over the square root of n. All right, I think that's the one I want to compare it to. Okay, so if you think about this, this is the same thing as 1 over n to the 1/2, okay, which makes this, again, a p-series that I'm comparing it to. So it's a p-series, and in this case, p is equal to 1/2, which is less than 1, so therefore, in this case, it's divergent. Okay, it's divergent. Now, thinking about that, b sub n, if it's divergent, is doing this. If I can show that a sub n is greater than it for all of n, if I can show that case, or logically deduce that, then I've proven that a sub n, by comparison, is also divergent. Okay, so think about this. If the only difference between a sub n and b sub n is I'm subtracting 4 underneath the radical. Okay, that's going to make the denominator just a little bit smaller, therefore making the fraction a little bit bigger. So logically speaking, a sub n is indeed greater than b sub n. So that being the case, everything matched up the way I wanted it to, I can say since a sub n is greater than or equal to b sub n, and the summation n equals 1 to infinity of b sub n is divergent. is divergent. Okay. Then the summation, well, by comparison test, I should say, by comparison test, then the summation n equals 1 to infinity of a sub n is divergent as well. Okay, so that's all good and done there. Everything works out. Okay, but let's say for instance I had this as an example. Okay, let's say for instance I had the summation n equals 1 to infinity. All right, of 1 over the square root of, instead of n minus 4, how about it was n plus 4? Okay, let's say that's the case I have, and I do b sub n, and I choose the same thing, this 1 over the square root of n. Well, I know before, based off of my logic above, I know that b sub n is divergent. Okay, and in order to use the comparison test, b sub n, if b sub n is divergent, it must be less than a sub n. But in this particular case, the plus 4 is going to make it kind of the reverse of above. It's going to switch this inequality. It's going to make that fraction on the left just a little bit bigger of a fraction. Okay, so it changes the inequality symbol. Now, this does not match up with this. Okay, so like if I were to draw this out, for instance, b sub n is right here, and it's doing this, it's divergent. But a sub n is less than b sub n, so it could be divergent, it could be convergent. I don't know what it's doing. I can't use the comparison test in that case. Okay, so if you get to this point here where the inequality doesn't match up with your comparison, okay, there is a way around that. There is a way that you can still use the comparison test. It's a little bit different of a setup, and it's very, very similar to the ratio test. So that's what we're going to be doing next. All right, so using something called the limit comparison test. The limit comparison test. So very, 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 very similar, but now we're discussing it as a limit. And this is, you're going to notice, very, very similar to the ratio test. It can be very mixed up with the ratio test. You just got to be careful. All right, suppose we have the summation of a sub n and the summation of b sub n. B sub n still being the one that we're creating. Okay, and they're all positive terms. Then, if the limit as n approaches infinity of a sub n over b sub n, which we've seen that before with the ratio test, talking about a sub n plus 1 over a sub n. Now it's a little bit different. It's two separate equations. If that equals some value c that is greater than 0, then either both converge or both diverge. Okay, so it's still important to know what b sub n does at the very beginning. So, so let's look at an example with that real quick. Yes. Okay. Cool. So something I have been saying for all of these, but something to keep in mind is I did always say that we should do the test for divergent as the first test always. But for all these examples, just to kind of save that step of us writing, I'm just going to go ahead and tell you the test for divergent for all these, the limit as n approaches infinity of a sub n, they're all going to equal 0. That all checks out. Okay, but just keep that in mind. That's always a good first test to try when doing tests for convergence and divergence. But anyway. All right, so it says test the following series for convergence or divergence. So I'm going to compare it to the leading powers that I got, which in this case, I'm going to make b sub n be 1 over 2 to the n. Okay. Now, just logically thinking about this, if I subtract 1, which is the only difference here for a sub n, if I subtract 1, that's going to make that fraction just a little bit smaller, which makes it just a little bit bigger of a value. Okay, so that's just logically thinking about that. Now, to discuss b sub n being convergent or divergent, that's still an important step. This 1 over 2 to the n is not, okay, I repeat this is not a p-series. This is actually geometric, okay? So if you want to think about this converging or diverging, you can think about it as n equals 1 to infinity of 1 over 2 to the n, which can be rewritten as 1/2 to the n power, because I can distribute the n to the 1 and to the 2, and I'll be left with where I started. Okay, so those two are the same thing. And what you could do is go back to what we were talking about with geometric series, and you can make n be the same thing as the power. You can do -1 +1, get it into the correct form, and just for a little bit of practice, we can do that. We can say the summation n equals 1 to infinity. I can say -1 +1, and that changes it to 1/2 to the n minus 1 power, if you really want to get it in the right form. But I'm okay with it being in this form till I talk about convergence or divergence, because what we're really concerned about is the rate here, that 1/2 and that 1/2. Okay, that 1/2, r, which is equal to 1/2, is less than 1, and therefore makes this b sub n convergent. Okay, but here's the thing: if I were to draw this out, okay, I know that b sub n is convergent. That's great. But unfortunately, in this case, a sub n is always greater than b sub n. I don't know what it's doing based off of the comparison test. Okay, so if you run into that issue, okay, I'm going to do this on the next slide, you can actually do the limit comparison test. So that's what we're going to do. We're going to show how the limit comparison test works. Okay, so I'm going to say limit comparison test. And I'm going to do the limit as n is approaching infinity, okay? And it's a sub n over b sub n. So the one we're given, which is 1 over 2 to the n minus 1, it was it 1 over, what was it? Yes. Okay, yeah, all divided by b sub n, which was 1 over 2 to the n. Okay. All right. We're good there. Now we just have to figure out what that limit's equal to, and if it's equal to a specific number and greater than 0, then that means they're both going to be the same test. So we know that b sub n is convergent. That would guarantee that a sub n is also convergent. And we'll talk about how to write that in a second. So let's see. I'm going to keep simplifying this. I'm going to say this is the limit n approaches infinity. I'm going to say 1 over 2 n minus 1 times 2 to the n over 1. Okay, which is equal to the limit n approaches infinity of 2 to the n over 2 to the n minus 1. Okay. Now, if I want to discuss what this limit is equal to, I'm going to show you mathematically how it's done, but logically, it's kind of the same thing. Logically, it's kind of the same thing as like your end behavior rules for rationals. It's like having the same thing on top and bottom. You take the leading coefficients, which in this case would be actually these just simplified down to 1. But I'm going to show how that works. In order to simplify that out, I'm actually going to take this 2 to the n as a GCF out of this quantity right here. This is actually going to be equal to the limit as n is approaching infinity. I'm going to have 2 to the n on top, and if I take a GCF of 2 to the n out on bottom, I'm left with 1 minus 1 over 2 to the n. Because think about what happens if I redistribute that 2 to the n. I'd be left with where I started. Okay, the 2 to the n's cancel out, and I'm left with the limit as n is approaching infinity of 1 over 1 minus 1 over 2 to the n. Now, if I think about where that's approaching as I go to infinity, this bad boy right here is getting an infinitely smaller fraction, which goes to 0. So I'm left with 1 over 1 minus 0, or 1. Now, the value is 1, which is greater than 0. Okay, so if you look back at the limit comparison test, that guarantees that they both either diverge or both either converge. And since I know b sub n converges, that means a sub n also converges. So I'm going to write that out. Since the limit as n is approaching infinity of a sub n over b sub n is greater than 0, which in this case is equal to 1, And also I know that the summation of n equals 1 to infinity of b sub n, the one I created, I know that that is also convergent. Okay, then by the limit comparison test, which you probably want to write that whole thing out, I know that the summation n equals 1 to infinity of a sub n is also convergent. And again, I defined a sub n and b sub n at the beginning of this problem. If you ever write this whole thing out, you probably want to expand what a sub n is and what b sub n is. Okay, I'll let you kind of pause that and think about it as you go. But it's not too bad. It's just trying to decide when to do it and what to do. So the math's not bad, just how to set it up. Okay. So I'll let you kind of think about that here for a minute. I don't really have, I mean, the rest of it's a little bit, well, it's not too bad. All right. Now, I know the problem is some people always have trouble creating b sub n, but listen, I'm telling you, if you just use the highest power of the numerator and denominator to create your comparison series, you're going to be set. Okay. And I always try to choose a series that's either that I know will either converge or diverge by picking either a p series or a geometric series. We've done examples of both of those in this lesson. All right. So let's look at another example. Yeah, here we go. Okay, so I got a rational here. I got a whole mess of stuff going. It's two polynomials, it's rational. Comparison test is not a bad way to start this one. Okay, and again, I'm gonna take the leading powers on top and bottom. Like on top, I got like an n squared. On bottom, I got like n to the fifth, but I'm also taking the square root of that. So that's like having. So let's think about that. If I make b sub n, it's going to be n squared over n to the 5 halves because it's the square root of n to the fifth. Okay, which if I were to simplify that down, just kind of reducing that, that's going to be what's this 2.5. I think that's just going to be 1 over n to the half power on bottom. Okay, now that is a p series. All right, again, that's a p series. P is equal to a half, which is less than 1, and therefore diverges. Okay, now I'll admit, if I'm trying to compare this function to see which one is always bigger than, let's see if b sub n is greater than a sub n or whatever, I will admit that this one's a little bit harder to do. I tested some points. I actually tested in my calculator. I tested just to see because this was a little bit harder for me. I tested n equals 4 to kind of see which one's on top always. And it came out that b sub n was actually greater than or equal to a sub n. Okay, so let's think about that. B sub n is the greater function and is diverging. I know that a sub n is less than that, and I can't tell based off of just comparing it. All right, I can't tell what it's doing, if it's converging or diverging, so that means we have to do the limit comparison test. Okay, so we're going to do the limit comparison test. So right here, I do an example of n equals 4 to test that inequality. All right, and that's okay to do. So the limit comparison test says I'm going to do the limit as n is approaching infinity of a sub n over b sub n. A sub n was 2n squared plus 3n over the square root of 5 plus n to the fifth. Okay. And I'm going to go ahead and do, so if I divide that by b sub n, I'm going to go ahead and do same change flip there. And I'm going to do times n to the 1/2 over 1. Okay. And, all right, if I were to simplify this out, multiply it out, kind of multiply these powers through, okay, that's going to be the limit n is approaching infinity. Let's see, that's going to be 2 to the 2 times n to the 5 halves if I distribute that, plus, I think that's just 3n to the 3 halves, yeah, all over. And then, oh yeah, it's just 1 times that, so I'm left with the square root of 5 plus n to the 5th. Okay, cool. All right, now I'm gonna do my rational rules to figure out this bad boy right here. So the highest power on top is 2n to the 5 halves power, and on bottom it's n to the 5 halves power as well because we're taking the square root. So because it's the same powers on top and bottom, I'm going to take the leading coefficients, and that's 2 over 1, which is just equal to 2. And 2 is greater than 0, so that means that I'm able to make a conclusion using my limit comparison test. Like if that was equal to 0 or less than 0, or not a number, not a constant, then I would not be able to make that assumption. But because it is, I can say, hey, since the limit as n approaches infinity of a sub n over b sub n was greater than 0, and I also know that b sub n is divergent, then by the limit comparison test, I also know that b sub n is also divergent. So there you have it. All right, worked out good. All right, here we go on that account. I got one more example I would like to do with the limit comparison test. Then we're going to move on to the error bound with comparison test, and then we will be done. Okay, and I am making record time right now. So if I'm going too fast, slow me down or pause me, but let's just keep going, baby. So right here, I got a sub n. I'm going to create a b sub n, all right, by taking these powers, these leading powers. And that's n to the 1/3 power over n, which if you reduce that down is going to be 1 over n to the 2/3 power on bottom. Again, this is a p series, okay, where p is equal to 2/3, which is less than 1 and therefore divergent. Okay, so if you were to compare these two together, if you were to compare this to this, it was a little bit harder for me to see as well. So again, I chose another example. I actually chose n equals 8, and I try to do it without a calculator. So if I test n equals 8, you get 2 over 12 in comparison to 1 over 4, and it works out that way right there. Okay, so a sub n is actually less than or equal to b sub n. Okay, which again, if I drew that out, here's b sub n. I know it's diverging. A sub n being less than that, I cannot make a conclusion using the comparison test. So the limit comparison test is my next best bet. Okay, so if I do limit comparison test, that's going to be the limit n approaches infinity of a sub n. Oops, I don't know why I did absolute value. A sub n, which is the cube root of n over n plus 4, divided by b sub n, which doing the same change flip is going to be n to the 2/3 over 1. Okay. Which, if I were to reduce this out, is going to be equal to the limit as n approaches infinity. If I were to multiply this out, I'd be left with just n on top, actually, I believe, because that's n to the 1/3 power times n to the 2/3 power. So that adds to n over n plus 4. And because we have the same power on top and bottom, I'm going to take the leading coefficients, which equal to 1. That's greater than 0. So because this is true, I am able to make a conclusion with the limit comparison test. And I am able to say that, hey, okay, so since the limit n approaches infinity of a sub n over b sub n is greater than 0, and b sub n is divergent. then by the limit comparison test, A sub n is also divergent. There we have it. We are looking good and ready to go. All right, perfect. So that's using the comparison test and the limit comparison test. I'm going to move on to the error bound with it, which is just using the same exact idea as the error bound for integral test. Okay, so let's look at this. This right here. Come on now, don't mess with me. Why is this not working? That's not good. Gummit. There we go. Okay. So what I just circled here in blue, that's what we learned with the integral test. We learned that the remainder falls within this bounds right here. And I encourage you, if you haven't watched the integral test lesson, to watch it to figure out how that works. Okay. And today we're going to be using this piece of it right here, that the remainder is less than or equal to the integral of n to infinity of f of x dx. Okay. So it says, if we have used the comparison test to show that this is convergent by comparing it to b sub n. All right, if I showed that it's convergent, then this is the case that I'm dealing with. I got that b sub n is doing this, and thus a sub n is also diverging. Okay, if I have that case, then to estimate the sum of a sub n by comparing the remainders, we can say that r of n, okay, which is dealing with the remainder of a sub n. So this is my remainder of what I'm talking about. We're going to say that that remainder, which is the difference between the sum and the partial sum, we're going to say that comparing it to the corresponding remainder for b sub n, which for some reason they choose as t sub n. So this is your remainder for b sub n. So we have those two remainders. Then since b sub n is greater than a sub n, since this is true, then that means that the remainder for b sub n is also greater than or equal to the remainder for t sub n. Okay, and if that's the case, okay, if this is the case, then we can also state this piece of the integral test and say that this is less than or equal to the integral into infinity of f of x dx, which this piece right here, t sub n and f of x, this is all dealing with b sub n, this piece of the integral portion from the lesson the other day. Okay, so we're going to use that knowledge to help us figure out an estimation for the remainder for a sub n, the one I'm given. Okay. Let's look at an example. Okay, I got two more examples, guys. Two more examples. And it says, use the sum of the first 100 terms to approximate the sum of the series, okay, 1 over n cubed plus 1, to estimate the error involved in this, and estimate the error involved in this approximation, okay. So we're going to use the sum of the first 100 terms to approximate the sum of the series, okay, and we're going to estimate the error involved in this approximation. So let's go ahead and do this then. Let's go ahead and figure out what the sum of the partial, so not going to infinity, let's figure out what the sum is of the first 100 terms first. Okay, I typed that in my calculator, and I got a rounded answer, I believe, 0.6865. That's the sum I got. Okay, we're going to estimate the error in that partial sum, okay, using this fact right here. So I want to figure out the error, estimate the error involved. So it's wanting me to estimate Okay. Well, if I'm going to estimate R sub n, then I'm going to estimate it by comparing it to some remainder T sub n. All right, and what that's going to be used for is the remainder of some series I create B sub n. Now, the series I'm going to create for B sub n using the comparison test is just going to be 1 over n cubed. And I know that this is convergent based off of the P series. Okay. And I also know that B sub n is going to be just a little bit greater than or equal to A sub n because of the fact it doesn't have that plus 1 in the denominator. Okay. So if you drew the picture out, you would see that B sub n is converging and A sub n is also converging based off of the convergence test. Okay. If that's the case, if A sub n, since A sub n is less than or equal to B sub n, I know that A sub n's remainder is also less than or equal to B sub n's remainder, right? Okay. If that's the case, then this inequality is true, and thus this inequality is true as well, n to infinity of f of x dx. And the reason that I'm choosing to look at this inequality right here is because usually the B sub n that we create is something that we can easily integrate. Okay, so I'm trying to estimate this using this formula here. So R sub 100, because we're talking about doing the remainder after the 100th term, is going to be less than the remainder of the 100th term with B sub n, which I know based off of the integral inequality is going to be less than or equal to the integral 100 to infinity of f of x, which is going to be 1 over n cubed dx. Okay. Now, for sake of space, I might skip a few steps with this because all I have to do now is figure out what this value is equal to using improper integration, and that's going to be my estimation for the remainder. So I'm going to say that R100 less than or equal to T100 is less than or equal to the limit as R is approaching infinity of 100 to R of, and in fact, I'm actually going to go ahead and integrate this. The integration of 1 over n cubed is going to be negative 1 over 2 n squared. And since I'm talking about f of x, I should really call that x. Okay, and I'm going to do that from 100 to r. Okay. Now, I'm trying to squeeze it all in here. Let's see if I can get it real fast. So if I do that, R100 less than or equal to T100 less than or equal to, if I do this limit out, I got the limit as R is approaching infinity of negative 1 over 2 times R squared, okay, minus the limit R is approaching infinity of negative 1 over 2 times 100 squared. This limit actually goes to 0, so it's going to be 0 minus negative 1 over, that's actually going to be 2 times 1,000 or 10,000, which is going to be 20,000. Okay, so plus positive. So if I were to simplify this out over here to the right, I'm going to say that the remainder for A sub n, which is less than the remainder for B sub n, is going to be less than or equal to, that decimal actually ends up being 0.000405. This is my estimated error for A sub n. It's going to be less than or equal to 0.0005. So that means that the sum of the first 100 terms is going to be pretty dang close to the actual sum. It's only off by 0.00005 at the most. Okay, so if I wanted to actually approximate the sum, I can say that, hey, the sum minus R, the sum minus my partial sum to the 100 term, which I have found at the top right here, so that minus 0.6865, I know that's going to be between negative 0.0005 and 0.00005. And I can estimate the sum within a pretty dang close range. So the sum is going to be between, I don't even know what that adds up to. I haven't even done that yet. It's going to be pretty dang close, 0.6865 plus negative 0.00005. I got 0.68675. And then over here, it's going to be 0.686. Oh, I messed that other part up. This should be actually 4.5. And then over here, it's going to be 0.6865 plus 0.0005. And I'm getting 0.68655. So you see it is pretty dang close approximation of what the sum is. It's only off by just a little tiny bit of a fraction. Okay. So this is technically my answer. This is estimating the error. These two are my, I mean, you can say either one. That's your, and then the bottom part here is actually estimating what the sum is. Okay. So there you have it. Let's try one more example and we'll call it for today. Okay. And it says in the previous example, which I had not shown this, maybe in a previous lesson I did, but we actually, okay, I'm telling you, I'm giving you that this is converging. So I don't have to, I'm not asking you to actually figure out what it converges, like if it converges or diverges, that's just already a given. But we are going to estimate the difference between the series and its fourth partial sum. So let's first figure out what that partial sum is equal to. So if I did the summation n equals 1 to 4, the fourth term, of 1 over n plus 2n, I actually got 0.640909, and that part's just repeating. Okay, so that is an estimation of my sum with 4 terms. Okay. Now, I'm going to use the comparison test in order to compare and estimate what the error is going to be between the actual sum and the fourth partial sum. And what I'm going to choose to do is, I know it converges, so I'm actually going to choose to do 1 over 2 to the n as my b sub n. And the reason I chose that and not 1 over n is because, first of all, 1 over n diverges, so that wouldn't be helpful. And 1 over 2 to the n converges. Okay, I know this converges because this is the same thing as saying 1/2 to the n, and the rate is equal to 1/2, which is less than 1, and therefore converges. So I'm going to use this as my b sub n. Okay. So what I'm saying is that the remainder for a sub n with 4 terms, that's going to be less than or equal to the remainder for b sub n with 4 terms, which, based off of the integral inequality, I know is going to be less than or equal to the integration of 4 to infinity of f of x, or 1 over 2 to the x dx. Okay. So let's actually figure out what that is. Okay, so we're going to do R4 less than or equal to T4 less than or equal to. All right, I'm going to say the limit as r is approaching infinity of 4 to r of 2 to the negative x dx. Now, if you can remember, integrating a to the x, okay, because it's negative, it's just going to make the integral negative, but integrating a to the x is actually equal to, so let's write it out. It's actually equal to, so a to the x, or in this case, negative 2 to the negative x, and then times by 1 over ln of a. Okay, so old school integral there. If you can remember that, hopefully you can, but if not, no big deal. Okay. Now, solving that out, we got R4 less than or equal to T4 less than or equal to. That's going to be the limit as R is approaching infinity of negative 2. All right, and again, sorry, I didn't write it right here, but this is 4 to R. This is going to be negative 2 to the negative r power over ln of 2 minus the limit r approaches infinity of negative 2 to the negative fourth power over ln of 2. Okay. Now, solving this piece out, I got that r4 less than or equal to t4 less than or equal to. All right, if I take the limit of this right here, the negative r power brings the entire quantity down to the denominator. And that's going to actually end up being negative 1 over infinity, or just equal to 0. It's going to be an infinitely smaller fraction. And that's going to be minus negative 2 to the negative fourth over ln of 2. Now, you can leave this as a whole quantity if you want, but I just typed it out in the calculator and actually solved it out. Then got that that's equal to 0.09016844401. So there is my estimation of the error involved with only using 4 terms. And notice how the error is a little bit bigger than the error in the last problem. The last problem we used 100 terms, so the error is going to be a lot smaller. But here we used 4 terms, so the error is going to be just a little bit bigger. Okay. And if you want to solve this out some more, you can estimate the actual sum if you want to, and say that like s minus the partial sum that we figured out earlier, 0.6400909 repeating. I know that that's going to be between, that difference is going to be between 0.090168 blah blah blah, and same thing over here, 0.09016 blah 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 blah. And whenever I added this quantity to both sides, I'm cutting off a little bit on my screen there, I apologize. But I'll let you kind of do that on your own. But all you got to do is just add the 0.6409 to both sides, and you'll get the same answer like you did before. Okay. So there's your kind of quick rundown, 52 minutes worth, I guess, of the comparison test, the limit comparison test, and then using the comparison test with the integral error bound in order to estimate the error when using comparison test. Okay. So take your time with this video, pause it when you can, retry the examples on your own. The notes are completed online, try the practice, but again, this was all optional because it's not going to be the final exam, but I would feel like I'd be cheating you if I did not give you this lesson. So congrats guys, y'all got one more optional video to go and then you'll be done with BC content and we will tackle this AP exam. So y'all have a great day.